you everyone for joining us. I'm Jeeves and I'll be your interview host for today. So, as you may be aware, or if you've been following us on social media, you'll see that this week is World Antimicrobial Awareness Week. So, today we have joining us Dr. Miraz Rahman from King's College London. He is a reader in medicinal chemistry and we'll be discussing a few topics related to antibiotics, antibiotic resistance, and a little bit about his research. So, Miraz, would you like to introduce yourself and just tell us a little bit about what you do?
Thanks for inviting me. So I'm Miraz Rahman. I'm working as a reader in medicinal chemistry at King's. My main research interest is in developing a new small molecule therapeutics against infective disease and cancer, as well as developing chemical tools to study antimicrobial resistance. I did my PhD at UCL, and I was originally trained as a cancer chemist. And then got involved in work with Cancer Research UK and set up spin-out companies. But now my main research focus is antimicrobial resistance.
Oh, that's really interesting. So can you tell us, now you've introduced antibiotic resistance, why is it so important? Why is it a topic that everyone should be aware about as well? And how does it affect everyone?
Antibiotic resistance is actually a major issue that some of us is not realizing that how grave it could be. COVID-19 probably gave you an example where you have got a pathogenic disease where you do not have treatment. And as you can see, the whole economy shut down, people dying at much earlier than normally people expected.
Yeah.
So antibiotics, which is probably saved most life since the medicine was first discovered, because it's involved at almost every stages in our modern medicine in therapeutics.
Yeah.
So I'll just give you one example, and then you will realize that in almost every minor infections, minor operations, you need an antibiotic to prevent infection. Think about in before antibiotic was discovered in say 1940s. Lots of people were dying just because, say, for example, during childbirth. The life expectancy, and in many cases, out of maybe 4 or 5 child, only 2 or 3 will survive. And now, as you can see, there is a much more because of the way our life is changing. You see a lot more cesarean section than the normal childbirth, and an antibiotic is almost mandatory because bacteria is everywhere. It will cause opportunistic infection. Now, if there is no antibiotic that can kill microorganisms, then what will happen that these infections can be simply life-threatening.
Yeah.
If you think about any other form of surgery, in every surgery, you need antibiotic to prevent infection, subsequent infections. And when you have antibiotics that do not work, and we are seeing in the clinic, there are many gram-negative pathogens which are resistant against multiple classes of antibiotics. So it is very worrying time because we are not finding new antibiotics while antibiotic resistance is on the rise. Although we are predicting that we might find some new antibiotics, but if the current situation persists, we will be seeing millions of people dying every year just because we cannot treat them with antibiotics.
Right. Okay. Yeah. So it's a very important topic. It's something that everyone should really know about as well. I suppose it affects everyone. So I understand that you do some work with Public Health England. Can you tell us a little bit about that work that you do in relation to antimicrobial resistance?
So King's and Public Health England signed a strategic agreement about in 2013 to identify new therapeutics and new chemical tools to study antimicrobial resistance. So at King's, my group, we are mainly focused on developing and designing new compounds, but all the microbiology is done at Public Health England.
Right.
And we have got about 8 projects currently ongoing with Public Health England. So that some of them are therapeutics projects, so where we are trying to identify new generation antibacterial agents which can work against multiple drug resistant and pan-drug resistant bacteria, mainly the escape pathogens focusing on gram-negatives. So these are the main public health pathogens, or antifungal agents against emerging pathogens like Candida auris, which has a mortality rate about 65% in hospitalized patients. So it ranges from 30 to 65%. And that's a very high mortality rate. So we are working on projects like that. There are other projects where we are developing chemical tools to study antimicrobial resistance, trying to understand why bacteria become resistant to different classes of antibiotics, how we can break those resistance. So we develop some fluorescent turn-on chemical probes that can be activated by specific bacterial enzymes. So when we generate library of those probes, then we can test them against different bacteria to link their antimicrobial susceptibility and resistance, because they will simply tell us which type of enzymes are present. And some of those enzymes, some of those proteins can be responsible for resistance. We also work on understanding bacterial membrane barriers. And we have recently a BBSRC funded project where we are looking at developing a bacterial membrane penetration rule. Because
Okay.
one of the main failure of modern antibiotic discovery is not finding drugs, not finding antibiotics against gram-negative bacteria,
Yeah.
because compounds cannot cross through the bacterial membrane. There's double membrane, there are efflux pumps present. So we are probing this membrane using both computational techniques as well as small molecules that can either disrupt the membrane or cross through the membrane. And then what we are doing is identifying chemical features in the structures which can be used to select what type of compounds can work against gram-negative membrane. And we plan to develop a rule. You might have heard about Lipinski's rule of five, which is used for drug likeness. So we would want to develop a rule that will govern that what type of chemical compounds, say, antibiotic discovery companies should be using when they are screening compounds against gram-negative bacteria. So
Okay.
that, so we are doing in a range of projects with them, and they have
Yeah,
been extremely supportive.
that's really good. Yeah. So I think you already touched on this, but can you tell us exactly what antibiotic resistance breakers are, and just about the new class that you've invented yourself?
So antibiotic resistance breakers are quite a wide-ranging class of compounds. One example is you might have heard about these beta-lactam inhibitors and beta-lactam antibiotics like clavulanic acid and penicillin or amoxicillin. So these compounds simply block the reason why an antibiotic might be ineffective and allow that antibiotic to work. So that's one class. So whether you've got enzyme inhibitors or suicide inhibitors you give. Another classes of compounds can be compounds which help to permeabilize the gram-negative membrane. So we have mentioned that compounds cannot get into gram-negative membrane. So if you use in combination with a molecule that can disrupt the membrane, it will allow antibiotics to enter and work. So that will be another class of compound. Another class of compound can be which are called influx pump inhibitors. So compounds get effluxed out, like the antibiotics get effluxed out, and that reduces the intracellular concentration. And then the bacteria can develop mutations to make that antibiotic ineffective. So efflux pump inhibitors can block the pump and allow the antibiotic to stay inside.
Okay.
So we are working on a different project, and this is the first proprietary technology or a patented technology that we have developed between King's and Public Health England, where we are developing compounds that can block their own efflux. So
Okay.
you don't need a second efflux pump inhibitor, but these compounds also act as an antibiotic. So we have got a single compound that can inhibit the target, kill the bacteria, and they are less susceptible to efflux. And that means you don't have to use two different compounds like a flux pump inhibitor and an antibiotic, because it's very difficult to use two, match their pharmacokinetics, and sometimes efflux pump inhibitors are too toxic. And they also do not block all the flux because the antibiotic remains unmodified.
Yeah.
So we developed a new classes of antibiotics that has been recently licensed to a company. So we are going towards preclinical development, and
That's
these
great.
compounds work against all the resistant bacteria that we see, particularly the gram-negative bacteria. So this is one of the main project with Public Health England at the moment.
Okay, so that sounds quite a lot of promising work then.
Yeah,
Definitely.
we are doing some innovative work to
Yeah.
tackle the problem.
Yeah, that's great stuff. So obviously you've done quite a lot of work in on the area of antibiotics. What would you say is your biggest accomplishment or maybe your greatest breakthrough in this area?
We are trying. Still early days.
Yeah.
We have recently published a new classes of broad spectrum antibiotics. So this is the first new class of broad spectrum antibiotics since fluoroquinolones, where they were published in 1960s. So we have just published in Journal of Medicinal Chemistry. They work against all known gram-negative bacteria. But I would say the biggest achievement to date is the technology that we have developed, which we call the antimicrobial resistance breaker or efflux resistance breaker, which can be used in all classes of compounds. So we have managed to identify a difference the way efflux pumps, efflux out substrates, and inhibitors block them, specific residues that can be targeted. And we are now designing compounds using our computational techniques to deliver compounds towards those residues where they can block efflux. So, as I've mentioned, we successfully developed one class of antibiotic. We are now using it to another class of antibiotic. We have also developed a new class of antifungal agents, which I've said the Candida auris, which is like there's no antifungal agents that work against them. And you look at the common azole antifungals, maybe the MIC will be 128 microgram per ml. On the other hand, the antifungal agents that we have developed, they have got an MIC of about 0.03 microgram per ml. So we have patented this year in February, just before the lockdown. And now we are talking to a number of commercial partners to see how we can commercialize this compound. So developing that technology is probably, we would consider, can revolutionize this discovery of antibiotics.
Okay, so as you've mentioned, none of this would be possible without technology. So with the technological advances that exist today, do you think it's possible for a new kind of antimicrobial to be found and authorized in the short term?
Possibly. It's the innovation is there, and we are seeing newer classes of compounds coming through. Just yesterday, there was a paper in Science where they have developed a new type of antifungal agent, and that works against some of the most difficult fungus. But I think the problem is slightly different. The problem is there is no economic incentive. So pharmaceutical companies are leaving this field where we know that the antibiotics, antifungal agents are urgent, and antimicrobial resistance is on the rise because they cannot make money out of it. So normal infections are acute indications. So if you take antibiotic for a week, you get cured, you don't leave any footprint. For the next 40, 50 years, you'll be living a good life. And the pharmaceutical companies cannot make money. While if you're a chronic indication like cancer, you will be probably taking the medicines for the rest of your life to make sure that the person is alive. And another problem is the government incentives are not there. And if companies are bringing in new antibiotic and then going bankrupt because they cannot sell, and which has happened to two companies recently, then this area will remain very difficult. So innovation will deliver new antibiotics, new antifungal agents. Whether that will reach market, I'm not quite sure, because this overall drug discovery is very expensive process, and no pharmaceutical companies will be doing charity. And so that means we need actually WHO and government interventions to create a global antibiotic fund, which will incentivize these companies if they can bring in antibiotic to the market.
Okay, yeah, so there's quite a lot of problems surrounding this area as well. There's lots of things to consider as well. It's not just as simple as doing a research and, take it forward.
I think the commercial incentive is the most important thing. That in the current system of capitalism, you need the commercial incentive to bring anything to the market.
Yeah, that's true. Okay, so that research and everything that you've spoken about is really interesting. One last thing, is there any message that you have to our viewers about antimicrobial resistance? Anything that you think that they should be aware of, people who don't necessarily have a scientific background as well?
Yes, I think you need to be more vocal. So you need to create awareness among your peers, among your family, among your, say, local representatives, to the media, that the antimicrobial resistance is an urgent issue. And after this COVID, when we hopefully get out of this pandemic soon, we don't want to be struck into another pandemic, which will be much bigger than this if the antibiotics do not work. So the steps that needs to be taken to fund research in this area, to incentivize people and pharmaceutical companies who will bring in antibiotic, and in general generate the awareness about the antibiotic resistance.
Yeah.
That's you can do. Talk to one person every day about antibiotic resistance. That will create the awareness. That's societal pressure that can probably will lead to these current government and other governments to take notice. They're aware of it, but definitely the pressure from the public is the best to make a major change in policy, and allow these innovations to foster, allow these antibiotics to be incentivized, because without that we are heading towards a very difficult time.
Yeah, you're right. Yeah, so as you said, awareness is so important. That's why we're doing this interview as well. It's so important to talk to people you know. And that's why we have a lot of educational campaigns going on as well. So keep
Yes,
an
this
eye
is
out on our
exactly the
social
right way
media.
forward.
Yeah, yeah, exactly. Well, thank you very much for talking to us about that today. Good luck with your research. We hope to hear a lot more from you in the future. And keep an eye out on our social media throughout the week. This is World Antimicrobial Awareness Week, so we will be posting things every day. Feel free to share them as well. As you've mentioned yourself, awareness is the first step, really. So thank you very much for joining us.
Thank you for having me.
Thanks. Bye.
Bye bye.